On to this session. In a previous session, we tried to do the perspective transformation. We had some issues with the reference points. Today, I'm presenting basically a new way of finding or basically selecting the reference points, which is not that different from what we had before. If you remember in the previous session, we took the hexagon points as our reference, or the half hexagon point that is used as a mask in our simulator or in our lane detector. And this mask basically is uh, selecting a region of interest in our scene, and we are using this region of interest and we are processing this region of interest. Now here it's the same, but this hexagon basically we need to, or the again the top half hexagon, we need to change its form a bit in order to present, I would say, the perspective projection of lanes on the road. What do I mean by that? If you look here at these different pictures or images that are saved during the driving or during the simulation, if I look at this one, we can see that we have basically just two lanes that they should be, of course, or they are in reality parallel, right? Because here we have straight basically route. And this is because, of course, of uh, the camera lens effect and the projection here, they are not parallel. And you can see that they would intersect, for example, at this point. And this is basically what we would like to do. We start from this position and we say, let's our hexagon look like this. So basically like this would be the first, I would say, link of the hexagon, then second, then third, and then fourth. Just presenting what we could see if we are moving in a straight line or a straight route. And this would be our basically hexagon that we can also use it as a mask as well. It's not an issue. And we would like to bring this back to the target or the destination for the perspective transformation. And that would be basically a rectangle. And rectangle would be, for example, looks like this. Because if this point or this lens actually, if I really looking at them, or we have, let's say, orthogonal projection, then they would be, first of all, parallel. And they would be like the two, let's say, sides or lengths of rectangle. So let's see what I'm talking about. So here I'm moving again to Colab. So we'll do first our modeling here, then we will put that in the Carla simulator and see the results. So what we see here is the perspective transformation. You see here some new parameters. So first of all, these two you know already. What we are doing here, we are just reading, or yeah, we are reading the image. Just 1 second, because I need to mount my drive because I have the images stored there. So this is my drive, and yeah, this is all the Carla images. Let's just copy the path there. Let's first import and see if we can read this image. We could read this image. Not good. Let me image show. So this is basically image number 2. And this is the size of the image, of course, that because we need it for the perspective transformation and also for other module we have with our lane detection. And here we define, if you remember, the source point and the destination point for the perspective transformation. The difference here is that the way we define the source and destination different from before. As I said, we will use also kind of top of hexagon there. Now it's just basically we have defined here 4 parameters that can be used to configure this hexagon. Now we have the bottom width, which basically the width, the as it is, that is basically the name. It's basically it is the width of the bottom of this half hexagon. And when you see here like 0.96, that means 96% of the width of the image width. Then here we have basically the mid width, which is again, it is basically the medium width, and here we have the height, and this is basically the height of the hexagon itself. And here we have the bottom trim, and the bottom trim is basically it's about the height, which means where is the starting of this hexagon. We previously started from 0, which means the hexagon starts from here, but in this case we are trimming, which basically we start, for example, from the 93% of the height. So basically the hexagon, for example, would start from here as an example. And here we see what I'm talking about. So we have this is basically our now mask. This is our hexagon in this case, and the width is defined by the bottom width. This is the height trim, which basically where this starts with respect to the height from 0, and we said it is 93% of the height, which means it is here. Of course, if you have 100%, it will start from there. Now this is basically the height itself, which means the height of the hexagon, of course. And then we have is the width, which is basically the 20%, this one, which is the width of the middle or the top, basically here link of the hexagon. Now what we see here is we're defining source point, and these source point are this one, this one, this one, and this one. This 4 points. This is our source. The destination, what we are trying to do is basically to transform this hexagon to this rectangle. And this is what I talked about, because if I project this, for example, rectangle on the road, then it's because of the perspective basically transformation, it would like this hexagon, and we are trying to reverse that. So basically we said that this point should be transformed to that, this should be transformed to this one, this to this one, and this to this one. Using this transformation, we would get something like this. So we get basically like almost parallel lines, because here actually anyway they are not parallel, but we will get now lines that we can use, if you remember, and we can process. And then the next step of the process in this step, in this case, is the histogram, where we actually try to find where we have peaks, and these peaks represent lines, for example, or the markers there, or the lanes, limits, and so on, whatever you would like to call them. And here we have basically the source and the destination. This offset is the same offset that we talked about, which is basically controlling the width of simply the width of that rectangle. So if I want to stretch them more, so basically I would have higher width basically, or longer width of the rectangle. So what we do here is to get perspective transformation from the source to destination, and this M is the transformation matrix. Then we wrap this perspective of the image. This is what we could see. Now this is for this image. So the one we had before was from different image, and for this image, and we have here like curvature, as you see. And basically when we do using this hexagon, we would get that now transformation, which is quite good, as you see. Now if I apply my histogram, let's here to wrapped image, then we will get this basically. And if I go from the middle and then I go left and right, we would get the right left lane, and this is the right lane. So this would basically, as you'll see later, would be filtered out using the sliding window search that we talked about, which comes in the next step. But let's check other. Let's take the image 26. Let's take it from here. I will remove this now just to make it faster. This image 26. It's like the opposite curvature. What happened now? Okay, interesting. Did I? Okay, this space was there anywhere, so I don't know. Anyway, so doing that here, and oh, let's delete this again. So 26, and this would be now the reverse transformation, and this would be my lens. So the idea there actually is that, okay, so from the middle, so we have right and left, let's say, peaks, right, of the histogram, and the first peak on the left and the first peak on the right, these are our lines. Okay. All right. So now in the next step, this is basically the just to see we have an issue there. I should turn this one go. So this is basically you see our original or basically source hexagon and target or destination, they are rectangle. Okay. Okay, so the next step here is the search, and what you see here is just a repetition of what we have done. So I'm just removing this out, and everything else I'm keeping it because I don't want to read the image. Let's start from here because actually I don't want to go up and down again, so we start reading from here. And anyway, these steps that you see now are the same, which means reading the image, configuring the source and destination point, wrapping them, and then after wrapping them, just copying the wrapped image to two destination images. And here we have the histogram, and here we are estimating the histogram. Now here is the just repetition of what we have done or what we have explained in the previous session. Here we had basically the midpoint of the histogram, and this we said that everything on the left we take the arc max, and everything on the right is basically be the left and right base. Now having said that, if we are talking about the max, this would be selected and that would be selected. And in any way, if we look here, actually, yeah, this doesn't represent that. These two represent this one. Yeah, just basically because there is this curvature, they split it in the middle. So I think they split it around. I think this. So we have here. So this starts from the middle, right? As you remember, which means it starts somewhere from here. Yeah, I don't know how is this estimated, because if I take from the middle, which is basically 350, then it would start from here. Then we have, yeah, one there, one, this one maybe, because there are two. This one, they are almost in the same line, is why they like accumulated like this. Yeah, that could be this, or this basically could be the reason. And we can try to see actually what created this histogram. Okay, so this is basically what has been actually taken from there. This one is that, and these two representing these two. And anyway, we would like to take the peak actually, which is this one, which is good because it's actually the starting of the lane or the line, sorry. And here yeah, so this basically the left base and the right base, which represent this point and this point, which represent actually this one and this one. And here we said, okay, now we have the sliding windows. So the sliding windows that would be cascaded from the bottom to the top of the image. And then they will be changing their lateral position based on how many pixels they see, or basically they are contained within this. First of all, they are contained within these windows. And then, of course, with respect to the position of these pixels. So if, for example, there is high density of pixels on the left side of a window, it would be shifted to the left. And the next windows also would be shifted to the left, unless we have an opposite direction, which basically means if we detect a high density of aerosol on the right side of the window, then it will start to be shifting to the right side. And the idea here is basically to start with windows from here and then start to follow this path, because we want at the end to segment all pixels that belongs to the left curve, and or yeah, curve here in this case, and all pixels that belong to the, or basically yeah, belong to the right curve there. And this is what we do here. So these are the windows. Remember, we defined the non-pixel or non-zero pixels, which represent all the detected basically. This is line markers. So all this would be now isolated, and we don't care about everything else. We take the, basically we are taking the position, the XY position of this non-zero pixels, and we start from the left, and so the first pixel or the first position of the left curve and the first position of the right curve. Then 20 here represent the width of the window. I'll show you now later, or the width of one of the windows, and all actually the windows, sorry. And here we have the minimum pixel, which means how many pixels as a minimum should be included or encapsulated within that window in order to move, or actually to perform an action, which is basically shifting left or right. Okay, here we will basically add now the left lane indices, which is basically all the lanes or all the pixels that now considered to belong to the left curve would be added here, and this basically all the pixels that considered to belong to the right curve would be added to that list. Now here we started with the first, for example, this would be, we have a loop over all windows. So we will have 50 windows there. And the first one would start really at the bottom of our image at the two locations, which are basically the left and right base location. Okay, so which we can start it from here. So basically the left X, which is basically the first position or the first point of the left curve, minus the margin, just basically to so the center is at the left X current. Then we here we subtract basically the margin to go to the first I would say the starting point of the window, which is basically here rectangle, and this is plus, so the other side, so we call it here x left, x left, L and low and high, sorry, and this would be now for the right curve, or basically the right lane. Now here we selected the good left indexes, we call, and here the good right indexes, which means here we are just taking, okay, give me all, or give me the indexes of all pixels that first of all they have values because they are all non-zeros, and they are located inside either the left window or the right window in this case. Okay, so what we are doing here, we are just adding them to the list, and there here we have if we want to draw these windows, we will do. In this case it's still false, but I'll put it at true to see how these windows will actually be moved or shifted in order to cover the lanes. And here the next is now if the number of pixels that are contained within the window is bigger than the minimum number of pixels, which is here 50, then we need to move, we need to do an action. And this action basically is just that we need to switch or shift. If you know an algorithm called mean shift, this is somehow doing the same. So our new position that actually will be used now for as a starting point for the next window would be the basically the center of mass or the density, center of density of these pixels. What the meaning of that? Let's say if I have this is my window. Let's say it's like, or let's plot it and then you see what I am talking about here. Just let me see if we select this true, then it will throw the out image. And here we don't plot yet the out image, so I'm just copying that all now, and here I'm adding just a cell where we run everything until that point. And let me now plot my out image here. Let's go. That is not the correct directory. This is actually then okay, so this one somehow failed, but the one on the right side we see that it worked on the right side. And what we have seen is that these windows, we have about 50 windows, as I've said. And what happens here is that you can see that these windows somehow are following the curve. And if we look here, just to give you an example, what happens there. Let's say we are at this point, or at now we are processing this window, and these are basically our left, or in this case they are good right indexes, which are basically the indexes of these red pixels. Now if the number of these red pixels that are inside this window is bigger than 50, that means we need to perform an action here. And what we do is we say, okay, now the starting point of the next, which means the center basically of sorry, the next window would be the average, which is basically here you can see the mean point of this red pixel. So if we have, let's say, red pixels that are detected here, this would be my starting point of the next window. And you can see it's quite on the center if you go to the left and right. Now this is how these windows would follow, for example, this lane in this case, and would follow that in this case. Now here they didn't, because of course we have, first of all, high curvature there, and yeah, they, for example, they did follow until this step, but here they couldn't find or capture that point. A solution to that would be to consider, of course, a bigger margin, which means we would have bigger windows, or here wider windows. So if I take not the 50, sorry, but I select here bigger margin, let's say 50, then I run, then you can see it is much better. We still need to add more, so we cover actually and we isolate all the pixels correctly. And here now, instead of 50, let's say we take 70. Okay, now we took all, so this basically now, this set of pixels belongs to the left lane, and this set of pixels belongs to the right lane. Okay, so maybe let's try to for another images just to make sure that we are safe enough. Yes, this is great. And I don't know, 10. Okay, great. And you see that we are actually, this is how we are canceling this noise as well. So it's great. Now we could estimate the correct length in this case. Okay, so what is the next step now? After we said that all pixels or all non-zero pixels that belongs to the left lane, which means they are inside this set of windows in the left lane, and we have also all the pixels that belongs to the right lane. What we can do now is we create kind of or we estimate a curve fitting, or basically we do polynomial fitting. This is what I wanted to say. So we do polynomial fitting along these lines here, or along this pixel there, and along these pixels here as well. What this polynomial is actually bringing to us, if we have the polynomial fitting, first of all, we can actually fill this gap between these here lines. And of course, if I know the polynomial model, I can get the curvature of that curve, and by getting the curvature, actually I can give this information to the controller to turn left or to turn right. I can also use it to predict the path and do the path planning, because if I know the curvature, I can actually complete this curvature, of course, and predict the path of the car in order to, for example, react faster, or to have like pre-reaction to the route. And this is what we will see, and this you will see what is happening down. Just let me first change this amount to, I think we are made it 70 and 50, right? Not this one, we have too many 50s. Okay, 70. Yeah, so after basically this loop of windows, you can you know that we have now the left lane indexes and the right lane indexes, and these are the non-zero pixels that belong to the left and non-zero pixels that belong to the right. Now, a second, sorry. Now basically we are just this is the non-zero x, remember, non-zero y. This is non-zero x, non-zero y. Just here we are just slicing them because we have other pixels that we had that they are non-zero. So this, for example, would be filtered out in this case, and we'll keep only what we actually have selected, and this is what is happening here. So we have the x position of the left line or curve, and this is basically the y position, and this x of the right and y on the right. This is just if you want to basically plot how many points are detected. It's not really important, but here what is important is the polynomial fitting. So we are basically we just take the second order polynomial fitting there, and we get here 3 coefficients of that basically polynomial. And this 3 coefficient would be returned in this list. So we have here the left fit list and the right fit list. And as I said, it is a list of 3 coefficients each one that basically identify the polynomial model of the left and the right. So here just a very important thing to consider, and I don't know if I talked about in the previous video or not, but what we are doing here, we are actually creating kind of a time series, you can consider, or a list of the coefficients. Now the idea of course, this time series or list of coefficients is that first of all, we can use it maybe later for as an input to, let's say, deep learning or machine learning models. So instead of using the whole image as input to, let's say, deep learning model to estimate the steering angles or to predict the steering angles or the steering or the lateral control basically input, what we do here, we basically follow the steps that what we have done so far, and then we take this the time series actually of the coefficient of the curvature of the left and the right lane, which represent the path. And basically, we can use that as an input to a simpler deep learning model. Well, I'm saying simpler because here my inputs basically just multivariate time series, which have here actually six time series together, or six variables in general. And we have, because we have three coefficients for the left and three for the right. And this time series could be used as an input to that deep learning based controller or machine learning based controller or any type of controller as well. Now here in our case, we're also using it for another purpose. We are using it to basically to, first of all, try to avoid anomalies in the prediction, and also to stabilize basically our detector here, our lane detectors. What do I mean by that? Here we are applying something called mean shift, mean shift, the moving average algorithm. Moving average algorithm, what it does is basically it creates kind of low pass filter, and which means it can to try to smooth your signal or your time series. So if you just here just Google moving average model, let's say, let's select yeah, this is not bad here. So the idea of the moving average, as I said, is to cancel out noise mainly and to smooth our signal. So let's say if we have here this signal, and this signal represents a coefficient of one of the coefficient of the light or the left lane, for example. If this coefficient is moving up or down like this, actually you would first of all you would see that when we plot the result, or when we plot the lanes and also the curvatures, you can see that it's really has high frequency and changing really dramatically, and we don't need to have that as an input for our control system, for example, or also we don't need a car to be very sensitive to that high frequency change. So by applying the moving average, we're trying to smooth and cancel out all this noise and just take basically the trend, the moving average trend of that. Now, this is basically the moving average. There is a drawback here that you need to consider, is that this basically noise that you're trying to cancel, it could be a sharp turn that the car needs to take. This basically sharp turn would of course cause a sharp change of the coefficients because the curvature is sharply changing there. This basically, if we apply the moving average model, we might miss the sharp left or sharp right or sharp change in the curvature. So I'm saying that, so we'll see that also later in the simulation if we change this moving average window size, because if we change this window size, we will actually see how much we are smoothing that. You would end up with a trade-off between cancel all the noise and having a stable estimation, but also missing, as I said, sharp curves or curvatures. And in order to have really smart, I would say, filtering of the abnormals or anomalies of the signal, and also knowing when it is actually just a sharp turn and knowing when actually that it is a failure in the detection, there are different techniques to actually to model this case. It's either using machine learning model, as I said, to consider the right signals and also to detect anomalies, and then of course ignore the anomalies. But also you can use other techniques in control like sensor fusion, and of course in this case you don't rely only on your detection. As I said, you rely also on other signals like maybe other sensors like LIDAR, or also GGPS, or also the radar, and then you can actually do these sensor fusions to know which signal we are getting is a noise and which signal we are getting actually something we need to consider. Yeah, we'll see the effect of that, but what is happening here is the moving average. And what is happening there is that we are taking the last 10 points, or the last 10 actually coefficients of, and so the first coefficient of the left curve, and here for the same for the second and same for the third, and we are averaging them. So we are trying to smooth this coefficient because we don't want to that curve to be changing actually with high frequency. And this is basically the window size that we need to control. So a bigger window size would end up with a smoother, basically, moving average, but of course, with less response to changes, I would say, or to immediate changes. So this is a trade-off that you need to look at when you run the simulator. Anyway, what we are doing here, we are averaging, as I said, we are taking the moving average of these three coefficients of the left and right curves. Then here we are applying the curve formula. So the first step is just to uh, create a line space, or actually this is uh, just basically here a kind of the index that we will send there. So if we have polynomial curve, we would have the x-axis and we have the y-axis, right? And let's say here polynomial uh, polynomial basically curve. I lost my connection. Anyway, we can do it here. So if I just take this and take these two, let me take this first just to show you what I mean there. Okay, so if I take this, you would see that this is just an index actually from 0 to 719, which is basically is the image shape 0, which means the actually the height of the image. So we are trying to estimate this curve, and this is our x actually, and y is there. So x goes from 0 to the 719, which is the height of the image. And we are trying to predict, of course, a curve, which is y, which represents, in this case here, the width axis of the image. And this is what we see here. For example, we have now, this is the, as I said, representing the x-axis of the polynomial fitting. And here we are with multiplying the first coefficient of, we have second order polynomial. So this basically would be the first term of the polynomial, which is the x basically here to the power of 2, plus the second coefficient multiplied by x, plus the third coefficient. And this basically would be for the left curve, and this would be for the right curve in this case. And this basically, if we take these two left and right curve, we get basically now our curvature. So let me try to, as I said, I want to copy this one and put it here from where we ended. Okay, and now let's take then this. Then I'll try to plot this. So you have this as an x-axis, and then would be this, for example, as the y-axis. Let's see if that works. Yeah, so this is basically our curvature that represent the left lane, and actually it represents in this case um, where was my left line? I don't know, maybe this one. I don't know if it's the same image again, we'll check. But basically it represents our left line if we go from 0 to 700. All right, and this, of course, also we have the right line as well. We can plot both, suppose, and this basically would be our left and right lanes. And this is basically the path of the vehicle. Now, the next step here that you would see there, and yeah, so just ignore this. Actually, this has nothing important. What we are taking now, we say that the curves and the lanes, this is also not very important for us, but what's important is the curves. Where we take the left fit x and right fit x, which actually contain the coefficient of the left and right curves. And this is also not important. Here what we do is we take the average. So the route, or actually the path that the curve needs to follow, is in between these two, right? So basically it would be like, what we are taking is the average of the coefficient of these two curves, and we are estimating our middle curve, which is basically the path of that vehicle. And this is what you see here by the mean. This basically, what I will explain in the next session, is how to draw now all these three lanes or three curves. I'll also draw something else, which is basically the target point, which is the end point of the middle curve. And by doing that, we can get these target points. We can use these target points for our controller, let's say for our pure pursuit controller, or also for the controller that the PID controller that Carla has, that I have basically presented in the second session of Carla simulations. Now, if we run this, yeah, I need to, again, this one I thought I would have changed it. It seems that I have changed it only here. Yeah, we didn't call the draw line function, which I'll talk about in the next part. Okay, so this is basically how it would look like. Now we see that this is the right curvature, this is the left curvature, this is the middle curvature, and this point is our target point that is at the end of the middle curvature, which we can use for, as I said, for the controller. And also we can use the curvature of this lanes as an input also to the controller. Thank you. We'll basically continue the next session. Okay, so welcome again. So as I said, in this session, I'll talk about the drawing function, how we draw the lanes, and also how we draw the target point. It is the simplest now part of what we have done so far. And we use what is called draw lanes function, which takes an image, which is our image that we want to draw over basically. And this is the point, or yeah, so it's basically the y-axis, or the width values of the pixels that belongs to the left lane. Okay, if you remember, this is basically the output of the polynomial fitting given the input, which is between 0 and 720. And this basically would be for the right curve, and this is for the middle, which is representing our path. Now this is our input for the polynomial model that we have seen. And this is basically just we are creating a zero image, and now we are basically stacking here, or creating 4 arrays. And what is the goal of these 4 arrays? At the end we are calling a function called fill poly, and basically this fill poly, the idea of it is to first draw this polygon, which basically represents the region, the left region of our lane, and this is the right region, which is in blue. This left basically it has vertices, which is, this is 1, 2 as a vertices, 3, 4, and then we have 1, 2, 3, 4. So we are first creating actually uh, the indexes or the location of these vertices. Then we are creating the location of these vertices and then location of these vertices. And this is basically what we have for. Middle is repeated twice because it depends where the middle is located. Either it's in the left of the polygon or it's in the right side of the polygon. And here what we see is basically we start with the left lane and the right lane, which is the two ends basically, and we are just first stacking the left fit, which is the indexes, as I said, of the left lane pixels, and this is the range here between 0 and 719 or 720. And no, 719, sorry, and in total there are 720 points. And what is happening there is that we are creating basically these four arrays. We are just transpose here basically for when it comes to the right, because just is in the opposite direction. The idea is that we, as I said, for the poly, we need to send vertices or points that belongs to the edge or the two ends of that polygon. And these two ends, for example, for the left side, they are first we have the left, which is here, that takes all the indexes, takes the coordinates actually of the left point. And here, together with the coordinate of the right side of that polygon, which is here our middle, which is coming from the middle fit. And this is now for the right one, it starts from the middle and goes to also to the right side. These points for the left pointer are, we can use them with the fill poly function in OpenCV. And we fill these two polygons with two different colors. One green basically and one blue. This we can also make it 255 to have really sharp green. And then we have here the contours, and what I'm doing here, I just plotting actually the middle line, which is the middle curve, which is the one that should come here, and you can see it there. So this is the red, this one is the poly, or actually the contour in this case that I am plotting. And for that we used draw contour from OpenCV, and this contour takes actually the middle L points. So in this case, this one or this one doesn't really matter, but we are taking, for example, these points that belong to that contour, or the coordinate of this point that belongs to that contour. And this basically would be the thickness. Maybe increase it to 10. And then here we have the color, which is here, actually the RGB color here, which is basically the R red, and this is blue and this is green. Okay, now what is happening inside draw lanes, actually this is the next important point, because now we are drawing on the after the perspective transform. So we are drawing on basically this view. Okay, what we want to do after we draw on this view is to inverse the perspective transform to actually bring back or project back what we have drawn on the street or on the lanes themselves. So for that we need to inverse, and it's actually exactly the same as what we have done before, but in this case we just switched here the source to destination, as you see, because before this was a source and this was destination. And in this case, this would be my source, and this would be my destination, and this is what we have done here. So we are just transforming it back to or projecting back on the street. Now, after we projecting it, we are just here drawing a circle at the location of the center coordinates, which is actually is what I'm taking here. I would say, yeah. So I'm saying let's take the first of all the pixel values that they have the value of 255 at the red part, which basically the middle curve. Then I'm taking the last point of, or actually the one that is that has the least height, because actually the height starts from zero from the top. Okay, or you can say that the point that is closer to the top of the image. And this basically my point. It is the target point because it would represent here that point. This is all the point along the curve, and I'm taking the last one, and this my last one is the one that is closest to the top. So there I'm drawing just a circle just to represent as my potential target point that I can use basically for example for the Q pursuit controller. Now just keep in mind that the coordinate of this point is not the world coordinate, which means it's not the 3D coordinate of the point in the real environment that you can really use for the controller. This is a projection of the point on the image plane. So in order to get the real 3D coordinate of that, you need to do basically camera calibration, or you need to use the pinhole model of a camera, or you can use the depth camera to estimate the destination, or actually how far is that point from the car. And then by knowing how far this point from the car, you can actually reconstruct the 3D location of it, because you know the XY and you know the depth, which basically then you can get also the 3D location of that point, and then you can use it as an input for your controller. Anyway, so what we have seen here is basically drawing this basically this two regions first, and plus the target point. I did some minor changes here, so let's run it. Okay, so this is basically the same, and it is working quite well. I tested here, I tested on the simulator, as also will do later, and in general it's working quite well. The only thing we need to handle, as I said, is potential noise or anomalies that may happen because of the wrong detection. For example, it might happen that our estimation might fail because maybe it would select this is as a left lane, maybe. Then you would have, for example, shaft left to the left or to the right, and that of course would, if it is used to control the vehicle, then the vehicle would go sharp left. And this is what we need to handle. And of course, the moving average model is one of the ways to cancel, as I said, this immediate, I would say, changes. But also it is, as I said, has drawback because if I get sharp curve, also that would be cancelled, and the vehicle would not be able to actually to turn on the right time. So it's a trade-off which can be solved using different techniques, like as I said, sensor fusion, using Kalman filter. If you are using information from other sensors, in addition to the sensors that we use here, which is a semantic camera, and or basically using an ML or machine learning models. So how we use ML model before going to the simulator and see how we can integrate this with the simulator. You can see here that we have this curve, and as I said, what we can do now over time, because we are concatenating the pixel values or these curves at every iteration. So what we will have at the end, like a time series, or actually we would have the whole curve that represent the path of that vehicle. So if I run, for example, the simulator using the autopilot for the whole course. So for example, that the car finished the whole course, and I store all the time my estimation of the lanes. This estimation could be perfect, could have some noise, like could, for example, jump up and down, like as I said, due to failure, or it could have, let's say, also sharp turns. Now, with that, I'm storing the control input, so I'm storing how the auto control, autopilot of Carla is giving actions. like for example, the lateral actions, mainly like steering left or right. Now, just remember, Carla is relying on the waypoint, which means a pre-planned path. So it knows the path. So it doesn't depend on vision like we do here. It does know the path already. So that one is following the correct path, and we are estimating the lanes using vision. And what we want to do, we have now two time series you can consider. One is the control actions, and one is the estimated curves out of the car. And what we want to do is basically use the estimated curve as an input and train a machine learning model, sorry, with the curve as an input, and output is the control actions that are coming from the perfect control of Carla. And by doing that, this also controller will learn to which type of, I would say, sharp changes would respond to. Like, is it really noise, or is it just continuation of this curve but actually just sharper, and so on. Okay, so this is a way of canceling or avoiding this kind of noise, I would say. Anyway, so in the next session I will move to Carla and just bring all that to Carla simulator or to the template file that we have, and we will see the result there. Thank you. As I said, in this part we will now integrate our new lane detection model with the simulator, and here I'm just doing what we usually do. So we basically move to the location of our example files, which doesn't always work smoothly. And then we need to activate our Carla virtual environment. We need to start our server. Then the first thing I want to do is to load my control simple environment, which is town 3. And first wait until it's open. Okay, again. So what we will see first is how it would look like, because I already integrated it, and then we'll look where actually I've done the changes. Okay, that's good. Then I will go to my lane not detection, but so this is the mask that I don't want to see. This is a depth camera that I'll show you now how you can also use it. And this is our line detection. You can see it's quite good in general. You'll see sometimes it might fail, but this is our target point. These are our segmented lanes. You can see the blue is basically just you can see also here on the curve it might fail, but actually it will correct later. And what is important is the target point. So if the target point is between the lane, then the car would not actually get out of the lanes, and it's not bad. Of course, this is what is trying to make the lane detection not working well, but in general it's not bad. You can see that the curvature actually is quite well here, and the car is following not the car actually following the car, but the detection is following the curvature correctly, because the car is controlled by the Carla controller at this point. Anyway, this is just the beginning, of course, of self-driving cars. There are a lot of things to consider, like in this case where we are at intersection and we have here a lot of lanes and lanes that are intersecting together. And for that, vision alone is not enough, or at least uh, like rule, or not rule based, but if we are using maybe machine learning model that it would recognize such scenarios, but in our case here is not. But you can see now it's actually doing not bad. As I said, we have here like sharp curve, and it is following that curve quite well. Now the blue here is, you can see, is the actually the overlay of our detected, let's say, markers on the street. And here we see our left and right region, and this is our middle curve, and this is our target point. So now we get to a sensitive place where where I was telling you that here comes the role of the correction parts, that either using sensor fusion or, here it did very well actually. I was afraid that it won't work it right. But here where the sensor fusion could be playing a role, just to avoid sharp changes in the position of the target point, for example. You can see, see it now, that happens here. And this, for example, where the controller in general, if you remember in the beginning, we talked about the PID controllers in general, and these PID controllers also, you can design them in a way that they don't react that fast, especially if we have the gain part, which is the proportional gain. If we try to reduce it, then of course the response will not be that fast to such sharp changes. So there are different ways, including the controller itself, and including if we are using machine learning or deep learning based controller. Okay, so this is what we would achieve at the end of this video. So I'll stop it now. Okay, as I said, it's doing quite well. And yeah, so some of the parts we have seen already here, and I just brought the updates actually of what we have done. Let's go to the render function of our HUD. Yeah, so this we have seen, dilation we have seen, and yeah, the first difference is that our mask, as I said, we have changed the hexagon a bit with these 4 parameters. This is the same what we have seen in the notebook, in the Colab notebook. And here I'm using it now as my mask, which would be used to segment or to represent the region of interest where we are actually estimating the lanes, which all up to here. Now then the difference would be now in the lane detection, which is the same function that we have used before, but inside we see the new differences that I've just brought from our Colab notebook. And here the differences start from wrapping. So we are wrapping the image now with basically the new hexagon. And here we can see that I have created a function called wrap image that takes our masked image, and then, which is exactly the image that you see as an input in the notebook. And if we go here, it is the same that we have done, which means we define first the hexagon parameters. Now here we have 2 options, like I'm inversing or not. Inversing would be used, if you remember, when I'm drawing the line, which means I'm inversing the process from after I detected the lane and I have drawn all the polygon and also the target point. I want to reverse to the or project them back on the street. This when it comes to inverse, it works true. And the difference between them is, like, here we have destination source, and this we have source destination. So we are just switching them. And then here we are applying the perspective transformation, and then here we are getting the wrapped image. Right, so This is basically the wrapping phase, and no, not here. Here, this is the wrapping phase, and the next we have, the next is basically, and the rest exactly the same as in the Jupyter notebook. Okay. Now the number of windows, I remember here we actually set it to 50. This is, I don't know if how that would change because we have already seen that it's not bad actually anyway. But this you can think that you can control, like the minimum pixel, the margin, the number of windows, and everything the same. Another thing you can control is the moving average. As I said, here we have -5. You can, if you play with this, if you put it like 100, then you would see that actually it's pretty stable, would be the detected length. But if you have sharp changes, like sharp curve, then it would miss it. It would actually respond like it have latency in response. And this basically, as I said, the trade-off of the moving, or actually, yeah, of the moving average parameter there. Rest is exactly the same. Everything here is the same. I only added the text that you have seen, or actually written the target points. So if we go here to draw lanes, if you remember, I have just here all that we have seen where I have drawn the circle. Just what I've done here, actually, I took the circle coordinates and plus 20 plus 20 here just to shift it a bit from the circle itself. Then we use also an OpenCV function. It's called put text, and here I'm just writing target points. Okay, so this is actually exactly the same. Now if I go to render, what I have happening here, I'm just actually have to try, except because at the beginning it might fail in detecting lanes, and I don't want to crash or the whole system stop just because of failure. So this is why we have the here error handler. And if it works, that's good. If not, just pass. And here we have we send the image, the raw image, and the mask, and we are getting back the output image and the raw image. And the raw image here would be actually the same image but with the lanes drawn on it. Okay, now just here you see something else, which is the depth image. And the depth image is an image, or actually a sensor, that you can use now to estimate the 3D location of that target point. Uh, because with the depth, you know how the distance actually. For example, if I run it again, so this is the mask. Just remember when I said mask, that would be sent also. I'm talking about this blue one, and this is would be now my depth, uh, basically camera or depth image. Of course, the closer pixels are to the car, which is here, they are darker, and the further they are, basically the brighter. And if my target point is there, this would be basically, I could get from this depth image the how far it is from the car. And knowing the 3D location of the car, knowing the target point, the projection of the target point on the camera plane that we detect here, which is this one, I could get basically the 3D location of that target point. And if I get the 3D location of that target point, now I can use it as an input to the controllers. And these controllers could be the pure pursuit controller, or could be just the PIT controller that Carla used, that I've explained in the second session, where we had the simple case where the car needed to drive straight along the waypoints. It is exactly the same. We're just need to give a different target point. Okay. So yeah, before I conclude here, because this would be actually my last for the self-driving cars lab. This will be my last session, training session. And the next session, I'll just explain to you what you need to deliver as assessment and in order to be evaluated. But in general, basically, what we have learned is, okay, using game Unreal Game Engine. Let's start first understand the control theory, how to do longitudinal and lateral controls. What is, for example, previous controller, what is PID controller, and what is Stanley controller, and basically how we can also, of course, use Unreal Game Engine to implement these controllers. In the second part, we learned about Carla simulator, which is built using Unreal Game Engine. So most of the you can see here the terms that you see and terminology, they are the same as like Blueprint, for example. They are used within Unreal Game Engine. And what we have learned, okay, now we have controller is one part, but the other part is the reference to that control, which is basically could be the path that this vehicle need to follow, could be the speed, of course, for the longitudinal control. And for the lateral, it would be the path and would be the target points. And what we wanted to do is actually to estimate the target point using machine vision, using a combination between deep learning, which bring us the semantic segmentation, and some simple machine vision techniques after that to, as we see here, to basically to process the output of the semantic segmentation in order to get the lanes and get the target points. Now the next part would be, as I said, to get the 3D location of this target point and use it for the controller. Now for you, for the course, this is not crucial or not important, and actually um, it's yeah it is not that difficult to do. I will just give you some references in the on Moodle or in my last email just to explain you how you can do that. Now for your assessment, as I said, in the next session I will